I'm going to talk about center manifolds that depend upon parameters and how this relates to bifurcations. So we're going to look at a two-dimensional example to get us started. So these are center manifolds which depend on parameters. So we'll first do a 2D motivating example and then say more about the theory. And then we'll even look at the Lorenz system. So it's that famous 3D ordinary differential equation written about in the early 1960s that was the first system to show chaos in the modern era. So it kind of reignited the interest in chaos that had been there during Poincaré's time, but then with the advent of computers, we were able to start computing things that were chaotic. All right. So this is just 2D. Well, x dot and y dot. X dot equals, it's purely nonlinear. So we've got xy plus alpha x cubed plus beta x y squared. Y dot equals negative y plus gamma x squared plus delta x squared y. So reviewing, x and y are the variables. And this is terminology I'll tend to use. They're the things that can change in time. And then the other things like alpha, beta, gamma, delta, these are parameters. And by parameters, I mean the things that during the evolution of the system are considered to be fixed, but we can also imagine that these things can be tuned and there'd be another set of parameters. So if you change alpha or change beta, you've got a different system. And how does the phase portrait change? How does the stability of the origin change? So yeah, by the way, notice the origin is an equilibrium point. And we can ask, what is its stability? Well, you'll notice the linearization is just like this, right? That's the linear part. If we were to write this as x dot, y dot, then that's the linear part, and then everything else is second order or higher. So we have due to this -1, we've got a stable manifold, and then we'll have an eigenvalue 0 because this is a diagonal matrix. So we have a center manifold. So we have a system where the y direction is the stable subspace, the x direction is the center subspace, but to really get at the stability, we're going to have to figure out the center manifold and the dynamics along that center manifold. All right, and it will depend on parameters. So how will we, following the procedure that we've been using, the center manifold will be approximated by a graph. Y equals h of x, or if you a function of the y versus x. And we're going to use our approach of approximating h of x using a Taylor series expansion. There's no linear term, there's no constant term. The first term is quadratic, just like last time. And then bx to the cubed. And then let's just go up to, we'll only approximate it to third order explicitly. Then we substitute this expression for h into the tangency condition. Which in this case will be, it's just partial h, partial x, x dot minus y dot equals 0. Where we then substitute in x dot and y dot from the ODE up here. So what do we get? Well, partial h, partial x to a x plus 3bx squared plus something of order 3. So that's the partial h, partial x term. Now x dot is, what do we have? Yeah, okay, x times y, and every time we have y, we substitute in y equals h of x. So then we put in this right-hand side. So we'll get a x to the cubed plus b x to the fourth. Okay, that takes care of this first term, x times y. Then we do the alpha x to the cubed term plus beta x, and now this is a y squared, so there'll be a, let's just collect all the terms here. It's a squared x to the fifth, and then there'll be higher order things. Okay. Hopefully this is enough. And then it's and then we do minus y dot, which means we'll have other things that are pretty high order. Well, is that true? Wait, we'll have minus y, so that would be plus a x squared plus b x cubed minus gamma x squared. And then this other term, delta x squared y, it's going to be order 4 or more. And then all of that equals 0. So it's not clear that we're going to need things of order 4. So we might even just throw this out. This is also order 4 or more. This is order 4. We don't know if we're going to need it. All right, so multiply everything out and then collect terms in each power of x, starting with x squared. And what will we get? Well, we'll get a minus gamma equals 0. So this tells us that a equals gamma. X cubed term, well, we're just going to have b equals 0, right? And you might be wondering, where is all of this coming from? It's really just coming from this part. Because if you multiply this bracketed term, the first bracketed term, and then the second bracketed term, that's going to be order 4. So none of that is even relevant. We didn't even have to do those, but maybe we didn't know that ahead of time. So, okay, b equals 0. And that means that to leading order, h of x equals gamma x squared plus, there's no cubic term. There might be an order 4 or higher term. Okay. So now we can get now that we've approximated what this, what the center manifold looks like, and it does look like a paraboloid, and depending on the sign of gamma, it's either pointing up or it's pointing down. Now we can get the dynamics along the center manifold. All right, so dynamics along the center manifold of the origin are given by, well, it's the usual approach. U dot equals AU plus FX Y. Sorry, instead of X and Y, we have U and HU. Really just, you take this first ODE, and in place of X, you put U, and in place of Y, you put H of U. And what do we get? So we get U dot equals U, H of U, plus alpha U cubed plus beta U times H of U squared. And what does this end up giving you? We get A plus gamma U cubed plus that's alpha. That's alpha plus gamma. Alpha plus gamma. And then there's no U to the fourth term. This would give us a U to the fifth term. So for now, let's just ignore that. We don't necessarily need that. Okay. So we've got this parameter, alpha plus gamma. Let's just combine those into one parameter that I'll call mu. Hopefully that's not too confusing. U dot equals mu U cubed to leading order. Where mu is defined as alpha plus gamma. All right, then we could look at different possibilities to find out what the stability of the origin is. And it depends on the sign of mu. So if mu is less than 0, let's just plot what U dot versus U is. And remember, what is U? U is it's like a curvilinear coordinate along the center manifold in a small neighborhood of the origin. So it's just giving us dynamics along the center manifold. What is the plot here? It is, this is a cubic polynomial, and then it looks like that. So that means to the right of the origin, U dot is negative, right? It's negative. So that means the vector is pointing to the left, pointing back to the origin. And to the left of the origin, U dot is positive. So the vector field is pointing towards the origin. So that means the origin is stable. All right. If mu is greater than 0, well, then we have the opposite sign for our cubic polynomial. We do it in the same color. All right, and now the origin is unstable. So is that clear? So if we were to summarize what we've got, we could do, we could summarize in terms of a bifurcation diagram.
What happens if mu equals 0? Mu equals 0.
If mu equals 0, the stability of the origin is determined by other parameters.
Okay.
Yeah, because that would mean that to leading order, we don't get anything. So we would actually have to go back and calculate that fifth order term. And so probably one of the other parameters, instead of just alpha and gamma being involved, maybe beta and delta will get involved. And we'll do that actually next, because there's another interesting part to this problem. So if we could summarize the stability of the origin using a bifurcation diagram, typically in a bifurcation diagram, you've got the parameter along the horizontal axis, which in this case is mu. And then you have along the vertical axis, you would put the location of the equilibrium point. And then often what people do is they will, they'll draw a solid line for stable and a dashed line for unstable. So I'll use orange. And what do we have? We have that for mu less than 0, the origin is stable. So I'll put a solid line and then maybe a little key. Solid equals stable. And then after that, for mu positive, it's unstable. And sometimes to remind ourselves what's going on, you could put kind of a vector field on here. So, okay, arrows are pointing towards the origin for mu less than 0 and pointing away from the origin. And then, yes, that question of what about at mu equals 0? At mu equals 0, the stability is determined by other parameters. I guess we should say higher order terms. In the u dot vector field.
Professor?
Yes.
So can we say something about more equilibrium points being created after mu becomes positive?
Well, not yet, because we didn't go to a high enough order to see that. But okay. Yeah, that leads into what I want to do next, which is look at the higher order stuff. So what did we do up here? We threw out a bunch of terms that we said, oh, it's order 4. If we actually included all of that, then what we would get for this term, this order 4 term, well, first we'd have to go back up here. And in approximating the center manifold, we would actually write, instead of just saying, oh, this is order 4, we'll include, well, let's look at 4th order terms and maybe go no further. Then we would, this c, x to the 4th would be carried around through the computation. And what we would end up with is this order 4 term becomes, well, I'll just for now call it c x to the 4th plus order 4, but we will have calculated what c is. C equals, and you could do this as an exercise if you want, negative gamma 2 gamma plus 2 alpha plus delta. So more terms get involved.
Should that be cx to the 4th plus order 5?
Yes. Yeah, it's always the next, it's just, everything that's polynomial of that order or higher, yeah. All right, and then if we carry through this computation even further, that means this thing that we left as order 5 will be something else. What will it be? Let me just write down here what u dot will be. We still have mu u to the 3rd. That doesn't change, but now we'll have an order 5 term where I'll just call it rho u to the 5th plus, I guess the next would be order 6. And rho is a whole bunch of things. Minus gamma squared 2 minus beta minus gamma 2 alpha plus delta. So all the parameters are now involved, alpha, beta, gamma, delta. And so then this will change what the vector field looks like. So what I did up here in the upper right, that will change. So if we, include higher order terms, then what do we get? For mu, I'll just do the mu greater than 0 case. For mu greater than 0, or maybe I should do it more carefully. Yeah. We've got u dot equals mu u to the 3rd plus rho u to the 5th plus terms of order 6. We could just separate out this, right? U to the 3rd mu plus rho u squared. So now notice this can equal 0 at not just the origin. So that implies the possibility of new equilibrium points showing up. So what do we mean? That means if mu plus rho u squared equals 0 at new equilibria. So that means u squared equals minus mu over rho. So we'll get, let's call them u star and plus or minus. This equals plus or minus square root the absolute value of mu over rho if mu over rho is less than 0. So we'll get some new things when mu over rho is less than 0, and also, rho cannot be 0. So let's just plot out what this looks like. What we'll have is that near the origin, I'm plotting the full space now, x, y. The center manifold might, it's dominated by that, the parabolic shape, but then there's maybe a modification due to the quartic term. But what we'll have is that there are new points. We've got the origin as an equilibrium point, but along the center manifold of the origin, new equilibrium points show up. U star positive, U star negative. And their stability will also be determined by parameters. So we can now summarize a more complete bifurcation diagram, right? This was our first attempt at a bifurcation diagram, and it leaves things to be desired because we don't know what happens at mu equals 0, and we didn't include all the higher order terms. So now we'll look at two cases: if rho is less than 0 and if rho is greater than 0. So if rho is less than 0, so what are we doing? These are bifurcation, updated bifurcation diagrams. And again, along the horizontal, we'll do, in this case, we're picking the parameter mu to write things with respect to, and then we're writing the location of equilibria. So like before, we will have, when mu is less than 0, we have a stable origin, and then we have an unstable origin from mu greater than 0. But then we get these two new points showing up, which are stable. And they would appear like this, right? So this is U plus, U star plus, and U star minus, where U star plus and minus are given by that. Like before, we could put in the arrows, and now the arrows and their continuity will make more sense because out of the origin comes these two new branches of points, and beyond them, things are still pointing towards the origin. But between the two, things are pointing away from the origin. That's just the case for mu equals 0. So, you know, we see richer possibilities by considering the higher order terms. And what about if rho is greater than 0? If rho is greater than 0, then the side on which we get the equilibria showing up switches. I'll still do mu, and this is location of equilibria. The stability of the origin does not change, so it's stable to the left, unstable to the right of the origin. But then we get the parabola opens in the negative mu direction, and they are unstable. And this would be our bifurcation diagram. You might say, well, how did I figure out the stability of these two other points? Well, we could have plotted, if we wanted to, what u dot versus u looks like. So, or no, u dot versus, yeah, u dot versus mu, and we could see. But there's also just by continuity of the vector field. If the origin, and we already know the origin is stable for negative mu, unstable for positive mu, that isn't going to change by including higher order terms. So that means the direction of these arrows is what it is. And so that means if they're pointing towards an equilibrium point, then that's a stable equilibrium point. So that's like the graphical method. But you could have also plotted, you know, u dot. So this is for mu greater than 0. We would have, I guess this will be having a 0 at u star plus. So that means the origin is unstable. And then you've got that stable u star plus, and same over here for u star minus. And we could do something similar over here, but I won't. All right, so does that make sense? These look to me like a pitchfork diagram. I don't know if they would meet the criteria for a pitchfork. Like, it looks like a pitchfork, but pitchforks typically don't involve the u to the 5th term. But I guess, yeah, since we're only kind of looking at this, maybe this is a pitchfork. So I will call it a pitchfork. And this case over here, where two new stable ones show up, is, I don't know why these get divided into two categories, but it's super critical, pitchfork bifurcation. And then over here, subcritical. I mean, it's not important that you memorize these things. So some key takeaways were that the emergence of new equilibria near an equilibrium that we already know, right? It's an assumption of this entire method that we're looking at the center manifold of an equilibrium point. So we already know that there's an equilibrium point. We've translated our system so that that becomes the origin. And now if there are any new equilibrium points that emerge near that initial equilibrium point, they must be along the center manifold of the original equilibrium point. And we have a nice method to determine their stability by looking at the vector field along the center manifold. And then you could summarize in bifurcation diagrams.
So if mu equaled 0 and rho equaled 0, we just need to keep going to higher order terms?
Yeah.
Now, if we were to do that, would there be a possibility of more equilibrium points showing up?
Oh, like, can you put a limit on the number of equilibrium points? I don't know. I don't know. Yeah, I mean, maybe there's another branch that shows up. It's possible. Yeah, so that's that example. Eventually we'll go to things that look like there's an analogy to the pitchfork bifurcation that happens if you have a 2D center manifold, and it is the hop bifurcation, which I think we'll be able to talk about in more detail later. But that's the case where, suppose we have here's a center manifold, an origin, and there is we have an equilibrium point, and it is unstable, so things are kind of spiraling away. You can have a stable periodic orbit being birthed out of any equilibrium point as parameters change. And this comes from the case of, if you have a center manifold where the linearization is a complex conjugate pair of eigenvalues, then as they go from, let's say here's our complex conjugate pair, as you change parameters, these must remain complex conjugate, but as they cross the imaginary axis from negative to positive, that means that equilibrium point goes from being sort of a stable sink to an unstable sink. And so we usually would write this as A mu plus or minus B mu, I B mu. If you have that for the linearization, plus there needs to be something special about the nonlinear terms, then you can get a periodic orbit born out of an equilibrium point. And we'll handle that in what's called the Hopf bifurcation, after a mathematician who studied it. And we'll do that later. But it kind of looks like a higher dimensional version. If this is our parameter, let's say mu, and you've got a stable equilibrium point, goes to unstable, but then nearby, I'm just going to sketch what looks like wow, it's pretty terrible. There's this parabolic, it's a paraboloid in the space, and things are like circulating around it. We'll see some more interesting diagrams later, but that's just a preview.
Does the periodic orbit exist concurrently with the equilibrium point?
Yeah, the equilibrium point's still there. It's just, and it has to be an unstable one. Otherwise, if both were stable, just the vector field wouldn't be continuous. Yeah. So this would be, I think what I sketched here would be this supercritical Hopf bifurcation, because you could also have the case of an unstable equilibrium point. And we've seen these are, Hopf bifurcations are special in the sense that these are robust to perturbations. Some bifurcations are very fragile. Like, unfortunately, the pitchfork it's fragile, meaning you're not going to see it in nature. Any small perturbation of the system, and you're not going to have 3 equilibrium points emerging out of one. You might have 2 equilibrium points emerging. So this is not structurally stable, but the Hopf bifurcation is. So there, you can see this in actual systems, and not just mechanical systems. It's seen in all sorts of systems. Yeah, we'll talk more about that later. What I wanted to do now is say something about kind of backing up, saying, okay, how do we carefully do analysis of center manifolds when you do have parameters? Because there is a tricky part to it. So this is the center manifold theory with parameter dependence. And this is in kind of starting on page 251 of Wiggins. So we have the same setup as before. We've separated out X variables and Y variables, which are the stable and unstable, well, sorry, stable, no, center and stable parts. So X is the center part. And so that means A is a matrix with eigenvalues of 0 real part. And then we'll have the function F that depends on X, Y, and epsilon is our stand-in for parameters. Y dot is B, Y. B is a matrix with eigenvalues of negative real part. And then we'll have a G. So this is everything that's second order and higher. It's a function of X, Y, and epsilon. And X, Y, and epsilon depend on, we've got R to the C cross R to the S cross R to the P. So we could have possibly P dimensional parameters. My headset is dying. I've got to figure out which one it is. Hopefully you can still hear me. No, that was not it. Let's see. Okay, can you hear me? Hopefully.
Yes.
All right. I can get away with one. I didn't plug them in last night, so they're pretty low power this morning. And those big headsets are just cumbersome. Anyway, okay, so we've got, the new thing is we have P parameters in a, if you want, a vector, epsilon. And we need that A and B do not depend on parameters. In fact, we're going to sneak in, we're going to secretly include a really lame ordinary differential equation, which is that the parameters don't change in time, but it's as if we're extending phase space to include the parameters. So we have a C plus S plus P dimensional space, but let's say for technical reasons, we are including this ODE just to remind ourselves that A and B do not depend on the parameters. So for example, a term like epsilon times X is considered nonlinear. So any dependence on parameters needs to be pushed into the F and G functions. All right, this thing, epsilon times X, would be considered a second order term, and so would be included in F. All right. So yeah, the same things as before. I guess I'll just say it again. Yeah.
So we could also do the same thing if, apart from the center manifold, we had an unstable manifold, right?
Yes, so it's just something we can mention at the end, that you can include the unstable directions, like a C, include some Z variables, Z dot equals C times Z plus H.
Right.
But then it doesn't have as much of a punch to do that originally, because then you already know the equilibrium point's unstable. But yes, you can definitely do that. And for mechanical systems, like I said, for Hamiltonian systems, the stable directions, there's as many unstable directions as stable directions, so you would have to do that. So that means you're not determining stability of the equilibrium point anymore. You're just getting at what does the phase space look like on the center manifold. And interesting things can happen on center manifolds, even if you have unstable directions. So yeah. So what was I saying? A is a C by C matrix with eigenvalues of 0, real part. And then B is S by S matrix, eigenvalues of negative, real part. Just like last time. I guess this is a difference though. A and B cannot depend on the parameters epsilon. You might decide that, okay, there is something that I will include in A and B because I only want to look at changes with respect to a particular parameter or particular set of parameters. So these parameters that we call epsilon are the ones that you want to look at bifurcations with respect to those parameters. All right, then you would do the same thing as before. You would approximate the center manifold as y equals h of x, but now you also include dependence on epsilon. And then take the time derivative of both sides. Y dot equals d, so we take the derivative with respect to the x variables, d h x epsilon, x dot, plus the derivative with respect to the epsilon variables, but then that's times epsilon dot. And since epsilon dot is 0, you don't have to worry about that. So very similar tangency conditions. And then you plug that into the original ODEs up here. So we get dx hx epsilon times ax plus f x hx epsilon minus, and then minus y dot. We're just rearranging this, right? Just like before. So minus y dot, that means minus b h x epsilon minus g x h x epsilon equals 0. So that's our main equation. Just like before, you can write h as a Taylor series approximation. And from this, you would equate equal powers, equal coefficients of your polynomial. And that would give you the approximation of your center manifold. So once h equals h of x epsilon is approximated, you could get the dynamics along it. So dynamics along the center manifold is u dot equals a u plus f u h u epsilon epsilon. And then just for good measure, we throw in that the parameters aren't changing. So this is the vector field restricted to the center manifold. Where we're thinking of the center manifold is also including these parameter directions. All right. So I think it's useful at this point to do an example, which we may or may not finish.
Okay, now I'm going to switch back to this other one. Okay.
And we're going to do the Lorenz system. So the Lorenz system is this nice system that's been looked at for a long time. And it creates that famous butterfly diagram if you choose parameters that people typically do. So we'll look at the center manifold of the origin. Which will, looking ahead, it will give us there'll be a pitchfork bifurcation. In fact, maybe I'll show the diagram just so you could have an idea of what we're looking at. And I'll include this whole part about the Lorenz system. So this is from a paper by Dodell, Osinga, and Krautzkopf. And this is it's a bifurcation diagram for the Lorenz system. There's this parameter rho, might be hard to see, but down the x-axis here is rho. And there's a triple point, so a pitchfork bifurcation happens at rho equals 1 at this point, P. And then there's these two branches, P minus and P plus. So the origin changes from stable to unstable, and then the other two branches become stable. And then you can see other bifurcations happen. This thing labeled H, a hop bifurcation happens. And it's, I think, after the hop bifurcation that you start to see, that's when the dynamics that are usually shown of something going around and then does something over here. It looks more interesting than that, but you get the idea. So what are the equations for the Lorenz system? Usually the parameter used is rho, but we're actually going to use something called rho bar, which is rho minus 1. So in my way of writing it, and this is the same as, if you want, I'm going to be following the example on page 253 of Wiggins. This is his example 18.2.1. All right, so we'll write x dot, it's a three-dimensional system. X dot, y dot, and z dot. X dot is sigma y minus x. Y dot is x minus y minus xz plus rho bar x. And z dot is minus beta z plus xy. So here we've got a 3D system, and we've got, for parameters, we would have sigma, beta, and rho bar. And just remember, rho bar, we're doing it that way so that the bifurcation happens for rho bar equals 0. And just looking at this ODE, we can see that for x, y, and z equals 0, the right-hand side is 0. So the origin is an equilibrium point. we don't yet know its stability. And we're not going to look at the dynamics on the center manifold as a function of all three of these parameters. We're going to view sigma and beta as greater than 0, but fixed. So they're fixed. We'll treat them as fixed constants. And then we'll consider rho bar as our, if you want, our epsilon parameter. It's the thing that we will look at change with respect to rho bar, okay? So these equations, you look at them, they're hardly nonlinear, right? We don't really have much in the way of nonlinearity. There's like this, and there's this. We've got the xz and the xy terms, but that's enough for all sorts of exotic behavior to happen. So you don't need much linearity to get, and this is the most studied probably nonlinear system there is because it was the first, 1963. And the way that we're doing things, this term will also be considered nonlinear, rho bar x. So, so with rho bar as a new, dependent variable in the way that we're going to view things, we're going to add the equation rho bar dot equals 0. So it's like we have something that's 4-dimensional, right? So then x, y, z, rho bar equals, all of them equal 0 is an equilibrium point. So let's look at the linearization. So the linearization, we've got x dot, y dot, z dot. So excluding the terms that I've circled up here, what do we got? We got minus sigma, 0, 1, minus 1, 0, and then 0, 0, minus beta. So that's the linearization in our original coordinates, which, so this has a block diagonal form. There's a 2x2 block and then a 1x1 block. So we could figure out the eigenvalues pretty easily. And the eigenvalues are, we've got minus beta, minus 1 plus sigma, and 0. What do you know? Okay. So we've assumed that sigma is greater than 0 and beta is greater than 0. So we've got S equals 2, a 2-dimensional stable manifold for the origin, and then a 1-dimensional center manifold. 2D stable, 1D center manifold of origin. So we need to compute the center manifold to determine stability of the origin. But first, we need the linearized matrix in that block diagonal form that we had from last time, right? Where we group things into, we'll have a 2x2 matrix B, and then a 1x1 matrix A. So we need to group things like last time. So group the 2 stable directions and 1 center direction. And how do we do that? We compute the eigenvectors corresponding to these eigenvalues. So the eigenvectors corresponding to the eigenvalues are as follows. First, for minus beta, we have a vector 0, 0, 1, the z direction. For minus 1 plus sigma, we get sigma minus 1, 0. And for the 0 eigenvalue, it's 1, 1, 0. So then we group these into our a transformation matrix. And here I'm gonna, I think following the terminology of Wiggins in this example, I'm using T instead of P. So how do we want to group these? We want to group these the center direction first. So that means we do this eigenvalue, the center direction eigenvalue first, 1, 1, 0. And then it doesn't quite matter what we do next. I'm going to choose sigma minus 1, 0, and then 0, 0, 1. Okay, so that's our transformation matrix, by which I mean we go from X, Y, Z to U, V, and W. Okay. And we'll also need the inverse. So I've already pre-calculated the inverse for you. So U, V, and W equals T inverse X, Y, and Z. And that is 1 over 1 plus sigma, 1 sigma, 1 negative 1, 0, 0, 1 plus sigma. The others are zeros times U, V, oh, sorry, X, Y, and Z. X, Y, Z. Okay. Then what? What did we call the, I guess let's label this equation just for fun, call it A. And now we're going to write U dot V dot W dot. It's going to equal T inverse A T, U, V, and W, plus we need to transform the nonlinear part. So what was the nonlinear part? We've got these things. We need to first write X, Y, and Z in terms of U, V, and W. And then we need to take T inverse of that. So we'll need to write T inverse of the nonlinear part, which is 0. And then I'm just writing those nonlinear terms in terms of U, V, and W. So this will be minus U plus sigma V W plus rho R U plus sigma V. And then down here, the last entry, U plus sigma V U minus V. Okay. We know what T inverse is. It's just going to be the, it's a diagonal matrix with the eigenvalues along the diagonal. So here goes, U, V, and W. So writing things now it's going to be in the appropriate form. We'll have 0, 0, 0, 0, minus 1 plus sigma, 0, 0, 0, minus beta. U, V, W. you work out T inverse times that thing, and this is what you'll get. 1 plus 1, 1 over 1 plus sigma times, and this is just a 3, it's just a column vector, but it has a lot of terms. Sigma rho bar U plus sigma V minus sigma W U plus sigma V, right? Because we chose the T matrix to simplify the linear part, but it actually makes the nonlinear part more complicated, which we'll address how to fix that later. But this is what you got to do. And then the last one, 1 plus sigma U plus sigma V U minus V. Okay, that's it. So we've got it now in the appropriate, if you want, block diagonal form.
Professor?
Yeah.
So in the line above the boxed line, you have a 0 for the nonlinear part of U dot.
Yeah.
Right? So why is there something non-zero term in the?
Oh no, it's the nonlinear part of X dot.
Right. So the nonlinear part of U dot is not 0.
So this, if you want, this is what we have here. This is that nonlinear part of T times U, V, W. We've just written every place that we had X, we wrote it in terms of U, V, and W.
Right, okay, yeah, makes sense.
Yeah. So this is what we have. We've got the ODE in the proper form for doing the center manifold computation. The center manifold is 1D. So how do we do this? Center manifold of the origin is 1D. So here's what we'll do. We'll say that the center manifold variables we'll call capital X, and it's just U. The stable directions, there's 2 of them, they're V and W. So we will write, you know, this looks like a departure, but hopefully it makes things make more sense. Y equals H of X. So that means this gets split into 2 things. V is a function H1 of U, and we need to throw in that it's also a function of our parameter. And W is another function, H2. These are scalar functions. So we haven't handled this case before. We've always looked at either like a 2D surface, but this is we've got a 3D system, and so we need to have a parametrized curve with respect to the other 2 directions. So that's what this is. All right. So for each of these, H1 and H2, we will make, we'll need to do a Taylor series approximation. So the Taylor series approximation, because we're including rho bar as a variable, we need to include that as in our Taylor series. So for this first one, let's say the first term, there's no linear terms and there's no constant terms. So A1 U squared plus A2 U rho bar. That's another second order term. Plus the last second order term, A3, would be if there is any dependence on rho bar squared. And then let's just stick with that. If we have to go to third order terms, okay, we'll do that. But those are all the second order terms. What about down here? Let's call this B1 U squared plus B2 U rho bar plus B3 rho bar squared plus terms of order 3 and higher. Okay. And then we've got the tangency condition becomes 2 scalar tangency conditions. And those are partial H1, partial H1, partial U dot minus V dot equals 0. And then we'd also have partial H2, partial U dot minus W dot equals 0. Well, this first one, if you work it out, then for each of these terms, U squared, U rho squared, you look at those terms and you'll see what their coefficients are. And they need to equal 0. So 1 plus sigma A1 equals 0. This implies, well, A1 is 0. 1 plus sigma A2, oh, something interesting, plus 1 over sigma equals 0. So this implies A2 is non-zero. Negative 1 plus 1 over 1 plus sigma squared. And the last one also gives us something boring. 1 plus sigma times A3 equals 0. Okay, A3 is 0. And repeat this for this second scalar tangency conditions, and I'll just tell you what it gives us. It's going to give us B1 equals 1 over beta, B2 equals 0, and B3 equals 0. So what does that mean? That means that along the center manifold, V equals H1 U, rho bar is this 1 minus 1 over sigma squared U times rho bar plus third order and higher terms. W equals H2 rho bar, and the only term is 1 over beta U squared plus terms of order 3. So in our space of U, V, and W, our center manifold is some curve which is given by this parameterization. The leading order. So then we can look at the dynamics along the center manifold. But I think we're just going to have to do that next time. And it's just a 1D ODE, right? So we expect we're going to get, it's going to be U dot equals something, and that something is going to depend on rho bar, and we'll be able to do some kind of bifurcation diagram. Just to leave you with some interesting images. I know it's already 11:15, but the Lorenz system, let me show. This is from a paper, and I'll provide it. It's showing the origin. I think this is for, yeah, it says up here rho equals 10. So that would be rho bar is 9. So it's pretty far away from what we're looking at. And so there's already something interesting going on here. There's two other equilibrium points, these things called P minus and P plus. And this disk down here at the bottom, the green dot is the origin, and the blue disk is the subspace, so the local approximation to the stable manifold of the origin. The unstable manifold you see is this curve, and it's kind of winding It's going away from the origin and then seems to be winding on to these P- and P+, which must be stable. This is showing these are different views of the stable manifold of the origin. I think it's for decreasing row. So up at the upper left, that's for the largest row. But this is doing, it's a group that does very careful manifold computations. So they're following it out very, very far from the origin. But if you started with any initial condition along here, it will go to the origin. So you can see there's a lot of rich stuff going on, a lot of twisting, and you can see videos of how things move. There's a video here. We've got lots of interesting videos showing what's inside. So let's see, do we get a peek of what's happening inside there? You can kind of see the butterfly diagram and how small it is compared to this giant sphere surrounding the origin that they've shown. So a lot of cool stuff. So if you have a chance, you could also read, Lorenz's original paper from 1963, where he thought he had come across a computer error, like why for two nearby initial conditions do I get something totally different? But nope, it wasn't an error, it's real. And then this group, Dodell, Krauskopf, and Osinga, they've done some really good work. If you're interested in how one computes manifolds, they've got an excellent group of papers about it. So they've used the Lorenz system as an example of how to do it. There's this other paper with more individuals, including Delnitz and Junge, where they do a survey of methods for computing stable and unstable manifolds, vector fields. But one of their main examples is the Lorenz system. I think that might be the only example in here. I'm not sure, but they got a lot of pretty things. You could see all the meshing that needs to be done to do this. But that's, oh, and then here's the box covering type methods. But that's just, if you're interested, looking for something to read. So that's it for this week. We'll finish up with the Lorenz system analysis, and then maybe I'll say something about including unstable directions, but we'll probably get to normal forms, either normal forms or center manifolds for maps next week.